Hi everyone, welcome to the second lesson on data straightening. So here is a set of data that we're looking at. P represents the pressure measured in kilopascals of a gas in a container, and V represents the volume of the container. So this setup would be something like a cylinder, and there's a piston which can squeeze downwards on the gas, so the gas particles contained down here inside the cylinder, and there's a way of measuring the pressure and the volume. So as the pressure increases from 100 up to about 150, it seems the volume decreases correspondingly. That makes sense. As you squeeze downwards on the cylinder, the gas would compress. Now our job is to find a formula linking these two measurements, these two variables. So like last time, we will use the Stats app on our graphing calculator. Now to save time, I've already been and entered the pressure in list number 1 and the volume in list number 2. As last time, if we check the settings, the first graph is a scatter plot using pressure in list 1 and then volume in list 2. Let's have a quick look at the raw data. Now that does look slightly curved to me. We could probably put a straight line there. Let's just do a quick straight line fit, and we can see the R squared is 0.990, and it does look pretty good, but there's a couple of little obvious spots there where the data is missing. So let's keep in mind that our straight line had a coefficient of determination 0.990. Well, 0.991 if we really wanted to round off, but that's going to be worth noting in the future for comparison. I don't think that was really, I think we can do better. So a quick plot of volume versus pressure. It seemed to me that it was slightly curved. Let's go back and have another quick look at that. If we have a quick look at that graph again, we'll draw in the best fit line. These data points here being under seem to suggest to me that there is a little bit of a curvature going on. If they were truly scattered and random, I'd be a lot happier, but they're not. So there we are. Now let's go back to our list. We are going to do the logarithm of each of these. So in list 3, I will calculate the log of list 1. And to remind myself, I'll put a little subheading here that is the log of P. So that's just a label. Now let's move across to this one. Remember, we've got to be at the heading, and I'll do the logarithm of list 2. Oh, forgot the brackets. Go back. There's and I'll put a little heading here. That's the log of V. Where are you, V? There you are. So there's my numbers for list 3 and list 4. Let's check the settings again. Always check the settings. Graph number 2 is set up to use list 3 and 4. That's what I need. So we'll just pop back to here and I'll hit graph number 2. Looks pretty good, like a straight line there. Let's do the straight line calculation. And we have a very slightly better. Last time it was 0.9905. Now we're 0.9906. Perhaps this wasn't the best example, but let's just go with it for now. So if I do the logarithm of V versus the logarithm of P, my data points did this. I had a straight line. The equation of my straight line is y equals mx plus c. Nice simple formula. My y variable is the logarithm of V. The gradient, if I go back to my calculator for a moment, the gradient A is negative 1.01. There is an intercept this time of 3.45. 3. And r squared is teeny bit better than the raw data, so we're going to go with this model. I might just go -1 and 3.4. How's that sound? -1 for gradient multiplied by my x variable, which was log p, and the intercept was 3.4. So, how am I going to rearrange this equation? It's not so easy this time. I can't just divide by log p because I've got this extra part sitting here at the side. So let's do this. I might use the power rule to write this as p to the power of -1. The coefficient can become a power. Now, it would be much more convenient if this was a logarithm added to another logarithm. So how could I write 3.4 as a logarithm? Well, that would be 10 to the power of 3.4. That would make it, logarithm of 10 to the 3.4 is 3.4. So that's how I'll do that. Now I've got log v equals log, and if it's addition of logs, it's 10 to the 3.4 multiplied by p to the -1. Clearly, because it's logarithm of both sides now, I can make the conclusion that v equals, now how much is 10 to the 3.4? Let's go and figure that out. It's going to be more than 1,000 because 10 cubed is 1,000. So let's just get to a calculation screen, and I want 10 to the power of 3.4. 2,512. So I have 2,512 multiplied by p to the -1. It seems like my formula is going to be 2,512 divided by p, and if you know anything about the gas laws in chemistry and physics, you probably would recognise this as an instance of Boyles' law. Boyles' law said that pressure times volume equals a constant, and in this case it seems that I could write my formula as PV equals 2,512, and that certainly looks like the form of Boyles' law that I learnt when I did physics and chemistry at high school. So there is how we do data straightening. We had an ever so slightly better coefficient of determination here. There must have been a little bit of too much rounding off in some of these measurements. Perhaps if I'd gone to more figures of accuracy here, we would have got a better curve. And importantly, this showed us how to deal with one of these where there was an intercept, a greater than 0 intercept. The last one we did, back up here, we had a beautiful 0 intercept, so that became a much easier one to solve. But that's good. Now we can handle ones like this where there is a gradient as well as an intercept on our linear model. Okay then, thanks for watching.